In section 10.5, this is going to be the last section of chapter 10 for us. So we skipped over sections 10.3 and 10.4, by the way. The last section we covered prior to this lecture was section 10.2. Now in section 10.5, we're going to do something that we've done earlier in section 10.2. That is, we would like to again make inferences for two population means. That's mu1 minus mu2. This time we're assuming we no longer have independent samples, so our samples are now paired samples. So in a way we are changing the design of our experiments. That's what we're doing, and I'll explain more in a moment. So what is the objective of our study now? We want to compare two population means just like we did before. The two samples that we are selecting actually in this section are not independent. Remember section 10.2 assumption was we had independent samples. We no longer have that assumption. Now here what we have is what they call paired samples or dependent samples. So what turns out the situation now is, as far as the design of our experiment goes, is that we have one set of experimental units or just one group of individuals. But what we're doing in effect though is we're collecting two pieces of information on that same experimental unit. Could be a subject or it could be something other than that. What we mean by experimental unit. An experimental unit is a unit that we apply what we call a treatment to it. So that's what an experimental unit is. So experimental unit could be a person, would be a subject. It could be a plot of land. It could be a house, could be an automobile, depends on what it is we're doing to those items. So our experiment, as far as our design goes, is called paired or dependent samples. That's what we're doing now. Now, here I have a list of examples for you. So in my first example, let's say we want to see the effect of diet, okay, on an individual. So what we could do is whatever diet that we are proposing, we can look at the weight of individuals who go on this diet, look at their weights before they go on this diet, and then measure the weights maybe a month or two later after they go on this diet. So that's the idea of pairing again. Notice it's the same person. So let's say on myself, they measure my weight before, then I'm going to go on this diet. They're going to measure my weight again. So notice it's the same experimental unit. It's myself, but they're collecting two pieces of information on me. Okay. So there is kind of a before and after treatment that's applied. Our treatment here is actually the diet, is what our treatment is here. Okay. Here's another example. Let's say we want to measure the carbon monoxide emissions of a group of automobiles. We can look at the emissions before we increase the oxygen level in the fuel tank, and we can look at the carbon monoxide emission after we add the oxygen to the fuel tank. So again, you have a before and after. Here the treatment would be application of oxygen to the fuel tank. And here's another example of paired experiments. Let's say we want to look at social or compare the social attitudes of twins. Now oftentimes twins are treated as one experimental unit because, at least physiologically speaking, and more so for identical twins, physiologically they're very comparable, right? Identical twins. So in effect you can think of them as one unit, or although there are two different people, but you can think of them as a paired group. So we can, let's say, have a child to stay home with their family, and then you can send another child to live with a, say, minority family for a few weeks, and then we can compare the scores on a questionnaire again, the idea is to measure their social attitudes of these. We try to compare the social attitudes of these two twins. Here's another example. Oftentimes, we may wonder if the ages of married couples, are they pretty close to each other on average, or does the man, for example, usually on average end up being older than the woman, or is the woman older than the man on average in a marriage? So this would be, this time, pairing the couples together constitutes a paired experiment here, and they're treated as one experimental unit. Here's another example. Let's say for this example now, we're looking at, we want to compare two different fertilizers. So we can apply fertilizer A on a plot of land, and then fertilizer B on the same plot of land, maybe just a few feet away from it, and then measure the yield of a crop on this plot of land. And I believe that's my next and last example here. Let's say we want to compare the rest pulse and run pulse on the same subject. So think about yourselves again. We could be measuring your rest pulse. That means you're sitting on a couch, measure your pulse. Then you're gonna, let's say, run around the block or around the house, whatever it might be. And then we're gonna measure your run pulse. Usually your run pulse is gonna be higher, correct? But again, the idea here is that if you want to compare the pulse rate, your rest pulse and run pulse, it makes sense to do it on that same experimental unit. Now, why do we want to pair, right? So why pairing? And here's what the reason is we would like to pair things. Because when we pair subjects together, in effect, we are removing the subject-to-subject variability from our data. Okay? And what that in effect does, that pairing results in a smaller sampling error. Okay? So if there's less of a sampling error, then any differences that we see in the averages is most likely due to the treatments. Okay? So that's why pairing makes sense. Now, conceptually, how are we going to do this? Well, because we have two groups, like we have two twins, or even you look at the rest pulse, run pulse. So the idea is measuring your pulse before you run and after you run. So I have it in our conceptual design as a before and after effect. So this is the distribution of scores before, this is the distribution of scores after. That the scores follow a normal distribution is a usual assumption, right? We assume normality since chapter 8. With those means and deviations, each has its own mean, each has its own deviation, but we are measuring the same variable, however. And then we're going to pair these together, the scores. Remember, because we don't have really independent samples, we have one sample. So we're going to pair them together. And as far as how we're going to do this, well, we're going to look at the difference between the scores before and after. Okay. So then we're going to look at the distribution of these differences, which is going to be normal again, because remember, the linear combination of normally distributed variables will be normally distributed also. So here the center of this distribution is mu d for difference, which is mu1 minus mu2. Now, this mu d, by the way, the difference, the average difference between the scores in the population is unknown and needs to be estimated. So how are we going to estimate it? A point estimate of mu d is d bar. That means we're going to take a sample. Okay, we're going to choose a sample, look at the average sample difference. That average sample difference represents the average difference in the population. Now this mu d I have here for you, these are individual differences. So I have millions and millions of individuals in here, okay, on which we're collecting before and after scores. And then from chapter 7, remember central limit theorem, we're going to actually take now repeated samples of size n from this population. And by central limit theorem, we have this, we've seen this in chapter 7. It's just our random variable now is d, which means differences. Now, once we do before minus after differences, then in effect, we reduce these two sets of scores into one set of scores, which we call the differences. And at that point, once we have one set of scores, then we can do a one sample t-test on the differences, that is. Okay? So, here is an example, and let's see how this is going to work out. So in this exercise, number 143, we're going to actually look at two exercises in this section. Number 143 is one of them. Okay, and then another one is very similar to this one. Would be exercise, this is 143 we're about to look at, and then we also look at number 145. Excuse me. Okay, so in this exercise number 143, it reads, anorexia nervosa is a serious eating disorder, particularly among young women. The following data provide the weights in pounds of 17 anorexic young women before and after receiving a family therapy treatment for anorexia nervosa. So notice again we have the before and after effect. These are the same individuals. So we are looking at their weights before family therapy and after. So just to look at these scores here. This is subject number 1, he or she. Before the family treatment, this individual weighs only 83.3 pounds. Pretty light, huh? And after the family therapy, it goes up to 94.3 pounds. Now, one thing we don't know is the age of these people, right? So I guess 83 pounds, that seems pretty light to me, right? I mean, some animals weigh more than that, right? A German Shepherd weighs more than that. But anyhow, we don't know about the ages of them. Maybe these are people in a certain age category because they're not awful heavy at all. But that's what these are. So the question, does family therapy appear to be effective in helping anorexic young women gain weight? Notice we are not told this is less than, greater than, or not equal to. So we need to interpret what does it mean for therapy to be effective as it relates to weight of these individuals. So, if I gather, because these are anorexic people, if an effective means success in this case, a successful treatment would be, or an effective treatment is if individual actually gains weight, right? So we would like to know if the average weight before is less than the average weight after family therapy. And that's going to be the basis for our alternative hypothesis. Now, what I've done to the right is I actually imported this data into Excel. And I did the column of differences. And notice in here, by the way, this is what we mean by one sample t-test. We have one set of scores here. So it seems like two groups in effect were reduced down to one group. So we're going to do chapter 8 stuff over this column of D. Okay? And also next to this I have done D squared column. The reason I'm doing this I'll show you in a moment. Because we have one sample and I'm given data, I need to find the standard deviation and I need to find the average from the data. Now, one thing I just want to have your attention here. So, what does a negative difference mean? What does a positive difference mean? And what does almost a zero difference means? If you look at point 1, that's pretty close to 0, means same weight, right? Before and after weights are the same. So, a negative difference, you look at the negative difference. The weight before is less than the weight after. So a negative difference indeed means higher weight after. And I have a smiley face here, right? That's actually an effective treatment, isn't it? So we would like to have differences that are less than 0, don't we? This is going to help me when I set up my alternative hypothesis. Is family treatment effective? That means, is the average difference negative, less than 0? That would mean higher weight. A 0 difference means weights are the same before and after. And positive difference, that means a lower weight afterwards. So for example, if you look at this individual, 3.8 difference. Before family therapy was 81.6. After family therapy, actually this person lost weight. So his or her family definitely did not help this individual much. Okay. In fact, they somehow hurt the weight of that person. Okay. Okay, so just wanted to point that out. So let's continue on. And in exercise number 149, which is a follow through with this exercise I just read, we want to construct a confidence interval. So first we're doing a hypothesis test, then we're doing a confidence interval. Now, here's the formula that we need in this section. So we are again comparing two population means. Our assumptions, notice by the way, are not the same assumptions quite as before. We still have simple random sample, but this time we have simple random paired sample. Remember that one? Because we in effect reduce the two samples seemingly into one sample, which is made up of differences. And then our normal differences, the differences follow a normal distribution, or the sample size greater than, or number of pairs would be at least 30. We have our alternative hypotheses, the usual two-tail, left-tail, one-tail test. And here's our test statistic. Again, in author's notation, this should have been what he has here. This should be subscript 0. That means our test statistic, assuming the null is true. And our decision criterion, again, is going to be pretty much the same as before. We reject in rejection regions depending on two-tail, left-tail, or right-tail. P-value criterion, p-value less than or equal alpha, we reject the null. Now here's where I want to have your attention to our test statistic. This is d bar, the average difference. This is S sub d. This is the standard deviation of those differences. That means, for our example, remember this is what d is. So we need to find the average difference here, and we need to find the standard deviation of this. Now, since I'm doing this by hand, that's why I'm going to go through the details with you. But StatCrunch actually handles everything. We don't need to do what we're about to do. So this is the criterion again for hypothesis test. And if you want to do a confidence interval, same set of assumptions we just had. And here's a formula for our confidence interval. So it's going to be d bar, the average difference, plus or minus a t times s sub d, which means the standard deviation of the differences divided by the square root of the sample size. And this formula is the same as the formula in chapter 8 that we had in chapter 8. Now, as far as how we're going to calculate the average difference, in chapter 3, we had this formula for the sample mean, right? So I'm showing you the formula that we are familiar with from chapter 3. X bar, you add up all the scores divided by the number. Well, in this chapter, instead of random variable X, we have random variable D differences. So notice the similarities. This tells me I need to add up all the differences divided by the number of differences. And these are the formulas we had for standard deviations. Okay. And just want to point this out again. In chapter 3 is what we have in green. And below it, we have a different variable now, D. So the process is the same process of finding the mean difference and deviation of differences. So, using the formula that we are about to do, D bar is sum of the differences divided by n. Sum of the differences was negative 123.5 by 17. So this is the average difference. Remember, the negative difference in this exercise was a good thing, right? Means a weight gain of that magnitude. So it looks like on average, family therapy helped the people, the subjects in this sample, in this research, gain 7 pounds. Sum of the deviation was that. Sigma d squared was that. I get these from my Excel output. And I'm plugging into this formula next. Okay. And there you have it. I did. And this is actually going to be now my standard deviation. The standard deviation of those differences turns out to be 7.157. Now the standard deviation, again, relative to the mean is in the 7 also. Deviation is almost as much as the mean. That just tells me that this data has high deviation or dispersion. Relative to the mean, that is. Okay, now as far as our hypothesis goes, remember we want to know if family therapy is effective in helping these anorexic women gain weight. And we agreed that the difference less than 0, negative difference, is what we would like to see. So you can actually write this hypothesis in 3 ways. You can say the average difference is 0, which means mu1 minus mu2 is 0, which means mu1 equals mu2. And these would be equivalent expressions for the alternative. Again, mu d less than 0 means the average weight negative afterwards, which again supports the idea that the weight after is greater than weight before. That's how you can get a negative difference. Mu1, average weight before, mu2, average weight after. And you can see that here also. The average weight before is less than the average weight after, which you can work backwards into the first line of the hypothesis, the alternative. Okay, I need the critical values. Remember, we get that from significance level, the size of our test, which the author gave us 5%, and the alternative here is less than. So our test statistic, in a moment we do. The critical value, because the degrees of freedom, by the way, for this paired t-test, because we have one sample now, or we reduce down to one sample, it's going to be number of pairs minus 1, n minus 1. So we had 17 pairs of numbers before and after scores. 17 minus 1 would be 16. So this is a t with 16 degrees of freedom. That's the t curve, because it's less than. So the cutoff point for our rejection region is negative 1.746. And again, here's how I got that number. I went to t of 0.5, 16 degrees of freedom, and 1.746. That gives me the right tail area. But by symmetry, the left tail should be the same, only negative t-score. So next, we're going to do our test statistic. And if our test statistic falls into that rejection region, we're going to reject the null. So I calculated our test statistic based on d bar that we found and SD over root n. Our test statistic turned out to be negative 4.18, again, which is rather high. So we have clear, convincing evidence that family therapy, and it's actually a negative score. So that means family therapy is definitely effective in helping these anorexic young women. Okay, and there you go. So because negative 4.18 is inside the rejection region, our decision is to reject. What's the conclusion? Remember, decision is pretty generic. You reject or you don't reject. That's decision. The conclusion is important. The conclusion is always in context of the word problem or in terms of the research. So our conclusion is family therapy on average seems to be effective. Remember, that's on average. We saw a case where family therapy actually didn't help one individual. That individual actually lost more weight after therapy. So everything we do is on average. So maybe I just add that on to this. So family therapy seems to be effective on average. Okay, the word average is important here. Okay, and let's do our p-value. And I'll show you how I got this in a moment. So once I ran this, the p-values for our t-test again, we always get them from StatCrunch. The p-value in this one is also 4 10,000ths, which is pretty small. So that means we have clear, convincing evidence against the null. We're going to reject the null hypothesis. Okay. Now, how am I going to do this using, using StatCrunch, right? We're doing a paired t-test. Okay, so I'm going to go to StatCrunch. Well, let me see if I did hypothesis test and confidence interval. Okay, and let's do this right now. Okay, so I'm going to do this in StatCrunch with you now. So I'm going to go to StatCrunch. This was exercise number 143. So I'm going to bring up that exercise. 143 is here. Okay, and this is the data on weights before and after. Now, we're going to go to Stat, go to T statistics. Okay, we're doing a T-test. And we're going to do this for 2 samples, right? And 2 samples. Actually, let's not do 2 samples. Let's go below it. Remember, we're doing dependent samples. So this is going to be a paired t-test. And here's a paired. The word paired is in here. Paired t-test. And the question is asking, okay, where is your first sample? The first sample is in the before. The second sample is after. And if you want, you can save the differences. Let me click on that just to show you what happens. But this is optional. And we're doing a hypothesis test. The mean is 0, means no difference in weights in this case. Against the alternative, we would like to research that therapy is effective. That means mu less than 0. And hit compute. Yeah, that's all we want here. Hit compute. And there you go. 2 things happened. First, you got the output. The other thing that happened is right here. See the differences I had in my Excel spreadsheet? We now have these differences here. And this is exactly the output that I had copy and pasted into my note. So that's how you get this. We can even do, since I'm here, let's do a confidence interval also. Let's see, our confidence interval is going to be 90%, right? We'll do it in a moment by hand, but let's actually run this in StatCrunch. 90%. So if I go options, edit, and instead of hypothesis, I'm going to go confidence interval and choose 90% and hit compute. Still under that paired t-test. And there you go. These are the answers. Negative 10 pounds to negative 4 pounds. Keep those numbers in mind, although they'll be inserted in my notebook. But anyway, this is how you do your confidence interval. Pretty straightforward. So on average, looks like family therapy helps these individuals gain on average anywhere from 4 to 10 pounds. Okay, let's go back. So we want to do a confidence interval, 90%, and I'm just going through the motions here. For 90%, alpha is 10%, half that 5%. Degrees of freedom, n minus 1, 16. And from the table to t-table, I can get that t-score of 1.746. Plugged in the numbers for a standard deviation and average difference, and calculated it to be, remember, that's the output we had. You'll see that output in a minute also. So this is our margin of error. And on average, looks like family therapy helps anorexic young women gain anywhere from 4 to 10 pounds on average. And we are 90% confident in that statement. And there you have it. So, now this margin of error, again, it means when we say on average, family therapy helps these anorexic young women gain 7 pounds. And I'm rounding these numbers, 7 pounds on average. That estimate of weight gain is off by no more than 3 pounds. That's the maximum error in that 7 pound gain in weight. The maximum error in that estimate is 3 pounds. And the error could go in either direction on the plus or minus side, give or take. And there you have it. These are the same numbers that you see here. I have 10.29, 4.26 negative, and there you go, pretty close. Okay. And so we're done with this one. Now, we're going to do one more exercise, and we're going to do this exercise entirely in StatCrunch, just to get more practice. And it won't take long once you go to StatCrunch, because we're going to skip over all the computational details. So in this next exercise, we're actually looking at something rather interesting. For this exercise, it reads, glaucoma is a leading cause of blindness in the United States. Then you have these researchers, Ehlers, measured the corneal thickness of 8 patients who had glaucoma in one eye but not in the other eye. Now note here, these are the same individuals, same subjects, not that all the same, but let's say myself, I'm one of these 8 patients. So suppose I have glaucoma in one eye, my right eye, and my left eye, I do not have glaucoma. So the point being, it's 2 measurements obtained on the same experimental unit, meaning in this case, on the same person, same individual, same subject. That's why pairing makes sense here. And by doing that, we are removing person-to-person variability. Rather than comparing, let's say, my corneal thickness for my eye with glaucoma with someone my age, my physique, it makes sense that to do it on myself, because behind the corneal in both eyes lies the same person. Physiologically, all other physiological aspects are under control. Okay. The results of the study were published. Here's the source of the publication, and the following are the data on corneal thickness in microns. A micron is 10 to negative 6 powers. So it's 1 in 10 million. 1 micron would be 1 millionth, not 10 million. 1 millionth. That's 1 micron. Very small measurement. So I went ahead and labeled these 2 populations. My population 1, these are the people with normal eye. These are the corneal thickness, measurement of corneal thickness for the normal eye. And these are the corneal thickness of the eyes with glaucoma. And notice patient 1, 2 is the measure in both eyes on the same person. So I called my normal eye population first, glaucoma eye second population. Now the null hypothesis, I have it here. The null says there is no difference in corneal thickness. Glaucoma or whatever, glaucoma is not a degenerative disease. It's not gonna cause any harm to corneal. That's what the null says. Remember the null, the hypothesis of no change, no difference, everything is the status quo. The researcher, on the other hand, here I have it in highlight. The question says, do the data provide sufficient evidence to conclude that the average, that means mu, average corneal thickness is greater in normal eyes. Remember, normal eye is now first population. Mu1 bigger than mu2, right? Greater means mu here is bigger than here. So that's why I have mu1 greater than mu2. And that means the difference 0 on the null side. Alternative, mu d is positive. So positive difference means thicker corneal for the normal eye. Now, and then of course in exercise 151 for the same data we're doing at 80% confidence interval. So again, I'm in need of finding the critical value. The critical value independent of data. We need the significance level of the test, that's the alpha, and the alternative, whether it's less than, greater than, or not equal to. In this case, it's greater than. So that means I have a right tail test. The rejection region is on the right side. True? So that's where my rejection region lies, right in here. The right side is the rejection region. And based on alpha, the size of our test was 10% right up here. See, 10% significance levels. So I went to a t-table right down here, and you can see I went to 10%, and this t has n minus 1. That's 8 minus 1, 7 degrees of freedom, and this is my t-score, 1.415. There it is. And so any test statistic equal to that or higher than that, we're going to reject the null. And remember, we're going to do this entirely in StatCrunch, and I'll show you how I got these numbers. But so judging from StatCrunch here, let me enlarge this. So our hypothesis test looks like our test statistic is 1, which isn't too far away from 0. So p-value is pretty large, right? It's not less than 10%, so we do not reject the null. And our confidence interval actually is to the right of that. 80% confidence interval is going to give us the lower limit, negative 1.37, to upper limit of 9.3. Remember, positive difference means thicker corneal thickness for the normal eye. So according to this confidence interval, the thickness could be in favor of the normal eye here, down all the way to in favor of actually the eye with glaucoma. Some of these people have thicker corneal thickness in the eye with glaucoma. So we cannot reject this null hypothesis. Now something interesting I want to show you here is this. This null I'm just trying to look at this side. When we look at this confidence interval, 0, the number 0 that's in our null hypothesis, the hypothesized value, no difference, is inside the interval. Usually you can test hypotheses using confidence intervals, and of course it requires you have a two-tailed test of hypothesis, by the way, because of that alpha over 2 business that we do with confidence interval. I don't have a two-tailed test of hypothesis in this exercise, but it's interesting. Even with that, 0 is inside this interval, so I cannot reject the average difference being 0. But again, I emphasize that should have been alternative, should be not equal to, and ours wasn't. Okay, so there you have it. Since 1.053 doesn't fall into that rejection region, we fail to reject the null. The p-value is also large. It's not less than 10%. So what's the conclusion? There is no difference in corneal thickness between the normal eyes and eyes with glaucoma. Okay, so that's the takeaway from this, and we're good in this section. So let me now just go and run this exercise in StatCrunch to show you how this is done, and we'll be done with this section. So let's see, this was exercise number 145. So I'm going to click on that exercise. And these are the numbers. So we're going to go to stat, t-stats, paired samples. You see that? Click on paired. Sample 1 is, that would be the normal eye. Sample 2, the eye with glaucoma. Now, let's see. Our hypothesis test here, we said we want positive, right? Greater than means thicker corneal thickness for the normal eye. Greater than, and compute. And this is how I got the output that you saw in my notebook. Our p-value is 0.16. And the mean, by the way, notice mean is 4. That means on the average, the normal eye is about 4 micron thicker. The corneal thickness in the normal eye is about 4 microns thicker or larger than the eye with glaucoma. But that 4 micron is not statistically significant in light of the standard deviation. Okay. So this was the hypothesis test. Let's do one last thing, would be the confidence interval. So again, I'll go to t-stats, paired. Sample 1 was normal, sample 2 was glaucoma. And then this time we did an 80% confidence interval. So I'm just going to put 0.8 and compute. And there you go. These are the numbers I got. The lower limit, negative 1.37, that means in favor of the eye with glaucoma. Thicker corneal thickness for this one. And the upper limit is 9.3, almost, call it 9 micron thicker in the normal eye, the corneal thickness thicker in the normal eye. And with that, we are done with chapter 10. So remember, in chapter 10 we only did 3 sections: section 1, section 2, and section 5, the one that I'm scrolling rather rapidly. There you go. This is a section that we just wrapped up. Okay, so hopefully you followed everything we did, and if not, please watch this lecture again and hopefully you'll get it the second time. Okay, and on that note, we are done with this section and with the chapter.